Hey everybody. So welcome to Unit 9. We're going to look at heteroskedasticity, and that's a big long word that means a changing variance. So you remember one of the key assumptions of the OLS model, one of the classical assumptions, is that the variance of the error term is a constant. So what happens if it's not a constant? What happens if it's a function of one of the variables in the data set? Well, we need to figure out how to test if that's going on, and if it is there, what do we do to fix it? So the second lecture this week will be about testing for heteroskedasticity. This first lecture will be, if we know we have a heteroskedasticity problem, how do we remedy it? Well, first of all, what does it do? It turns out it doesn't bias the slope coefficients, so they're still okay, but it does bias the variance estimates. So we have to make adjustments, otherwise our t-statistics and p-values will be wrong. So that's what we're going to look at. In this first lecture, we're going to look at what heteroskedasticity does and how to remedy it. And then the second lecture this week, we will look at the tests. So get your pens ready, everybody. We're about to start. Right, so we are talking this week about heteroskedasticity. It's kind of a long word, so let's break it down. So, what we've seen before, skedasticity means randomness or variation, and hetero means differing. So this refers to the assumption that the variance of epsilon is a constant. So that is the homoskedasticity assumption. And if that's not a constant, then we'll still write sigma squared, but we're going to put an I as a subscript. And we'll do that to indicate that every point in the data sample, every observation, the error term may have a different variance as we go along. So this is one of the classical assumptions. It's assumption number 2, if you recall from that list. That's assumption number 2. Let's just have a look back at the list of classical assumptions. So we have our regression model. So it's a multiple regression. Beta 1 x1 plus ... to beta k xk plus epsilon. And the classical assumptions, well, the first one is that the expected value of the error term equals 0, meaning on average your errors aren't systematic, that you have the correct form of the regression equation. Number 2, variance of epsilon is a constant. Number 3, the covariance of any two errors is 0. So the errors are independent of each other, the error terms. Number 4, that the error terms follow a normal distribution with a mean of 0 and a variance of sigma squared. And 5, the x's are non-random. The x's are non-random. Now, so these are the classical assumptions, and you remember that if all these things hold true, there are certain properties of the OLS estimator that we can refer to, especially the Gauss-Markov theorem, that OLS then gives us the best linear unbiased estimator. We're going to look at this assumption, and this assumption over the next couple of weeks. We're not going to revisit that assumption. That one may break down if you've omitted important variables in your model. So we've talked about omitted variable bias, but we're not going to revisit it right now. This assumption here, we list it as an assumption, and the textbook makes a few cryptic little comments about the fact that we don't actually need to assume that in all cases, because if you have a very large sample, then it's possible to use certain formulas for your test statistics that are true as long as you have a large sample, even if you don't know how the error terms are distributed. Because if you have a large enough sample, certain test statistics will converge to a normal distribution or a known distribution, even if the underlying error terms in this case, or the underlying random term, is not normal. That's an obscure point. It's called asymptotic theory. It is very important, but you don't need to worry about it for the sake of this course. Actually, you've seen an example of asymptotic theory. I'm gonna, if I can find my textbook, where have you seen asymptotic theory in operation? Well, you've seen it with the t-tables. Okay, so if you look at the t-table, degrees of freedom, so that's your sample size minus the number of coefficients you have to estimate. And then these are the critical values. Now, they differ from the standard normal critical values because the t statistic follows a different distribution, because we're taking account of the fact we estimate the variance or the standard error. But as the sample size gets larger, this critical value is converging on 1.96, which is the critical value for the standard normal distribution. What's going on here is that as the sample size gets larger and larger and larger, the t distribution converges on the shape of the standard normal distribution. So that's an example of an asymptotic result, meaning that certain test statistics can be constructed in such a way that even if they're not normal in a small sample, as the sample gets large enough, they converge to a normal distribution. Anyway, long story short, we're not going to look at assumption 4 in this course. We are, however, going to look at this assumption, this assumption, this assumption, in each case saying, okay, what if this is not true? How does that affect our estimates? And then how do we fix the problem if it's not true? So where are we in the book, by the way? We're in chapter 5. So we're going to follow along. However, in this case, I'm going to depart a little bit from the book because the book spends a lot of time talking about one way of treating heteroskedasticity, which is kind of old-fashioned and people don't really use it much anymore. And then it talks briefly about another way, which turns out to be the way that everybody uses and it makes more sense. Okay, so getting back to the underlying issue, suppose that the variance of the error term is not constant, which is, it's such a common thing that you can pretty much assume, at least in a cross-sectional regression, that it's probably going to be the case. So you've got your x data and your y data, and you might have an upward sloping relationship, but all that means is that the spread of the observations expands as x gets larger. And there are lots of cases where we would expect to see something like that. So for instance, we have data on, well, actually, that was a good example right at the beginning of the textbook. So you've got the output of power plants and the cost of running the power plants. And you'll notice that down here, the observations are all tightly clustered in, very small variance. And then once the output of the power plant gets larger, the bottom end of the distribution is down here, and the upper end is now up there. And as you get a larger and larger sample, the data is getting scattered farther and farther out. So another example, and one we'll refer to again, is the education data set. So let's say we have total spending on education in a country, and it's a function of GDP and population. That's our data. So we have education, total spending on education in country I. And then we've got GDP, which is the gross domestic product in country I. And we've got population. Well, it's pretty safe to say we're going to have heteroskedasticity if we run a regression like that. It's just not reasonable to think that if you have a country with, if you have a group of countries with a very small GDP, then the data is going to be clustered around there. It's not going to be the case that with the country with very small GDP, you're going to have some of your highest education expenditures. But as the data set gets larger, or sorry, as GDP gets larger, some of the countries will have a slow growth in education spending. Some will have a high growth in education spending. And so the spread of the data is going to be something like that. So that's the heteroskedasticity case. So then if you fit your line through the middle of the data, it means that the spread of the data around the line is going up. So how does that affect the properties of our OLS estimator? Well, we have to assume a specific form for the heteroskedasticity. So we're going to assume that the variance of epsilon equals another character, omega squared. It looks like a W, but it's actually a lowercase Greek omega. And then we'll have that times a constant sigma squared. So this is the part that changes with each element in the data set, and that's a constant. So, and we'll assume for the moment that we know what omega squared is, just so we can work through the math. So our regression model will be the simplest possible one. Now we want to know, is beta hat going to be biased or not? So we'll check this way. We have beta hat equals, so our usual formula, x, y over the sum of the x squared And we can use that formula on page 68 to break that up into beta plus the sum of x epsilon over the sum of x squared. So that's the star formula on page 68, which we've seen before. Now we take the expected value. Well, the variance doesn't actually appear in here, so nothing changes at this point. The expected value of beta hat equals beta as before. It comes down to taking the expectation of this term. We're taking the expected value of epsilon, which is 0. It still has a 0 expected value. We're holding that assumption. But the fact that it has a non-constant variance doesn't actually affect this calculation. So OLS is still unbiased. Hold on, I took that away very quickly. Give you a moment to scribble it down. OLS is still unbiased. The OLS estimate of beta is still unbiased. But we then have to estimate the variance of beta, or to get the standard area, the standard error. So what about the variance of beta? All right, so variance of beta hat equals the variance of, well, we're allowed to use the star formula, sum of x times epsilon over the sum of x squared. And so that will equal the variance of, now remember way back at the beginning of the course, the variance of a constant plus a random variable. Well, adding a constant doesn't change the variance. So we can just drop out the beta part here, and we have the variance of x times epsilon over the sum of x squared. Okay, and then this is a non-random term on the bottom, so we're going to take it out, sum of x squared, but we have to square that. And again, if you're not sure why, just look up from the beginning of the course the rules about manipulating variance expressions. So that's times the variance of the sum of x, and then we have 1 over the sum of x squared times, now what are we going to do here? Well, that's the sum of x times epsilon, so the summation, just in your mind, picture writing the whole thing out as x1 epsilon 1 plus x2 epsilon 2 plus x3 epsilon 3 dot 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 all the way down. And then you can factor out the x's in that expression. And so when you take them outside the variance, you have to square them. What we end up with is the sum of x squared variance. Oh, my pen's running out. So, and again, it's squared because we took it outside of the variance. And then we've got 1 over sum of xi squared, all squared, times the sum of xi squared. And that is times the variance here. And so that is, by assumption, sigma squared times omega squared. And then this is a constant, so we're going to be able to bring it outside. And what we'll bring it outside the summation there. So what we're going to end up with is sigma squared times 1 over the sum of xi squared, all squared, times the sum of xi squared omega squared. And we cannot cancel this and that. Not allowed to do that. So this is as far as we can reduce that expression. But if you run a regression and you use the OLS formula, R will print out, or it'll calculate that the variance of beta is sigma squared over the sum of x squared. All right, so you'll have a situation where this is the correct answer, but this is what the computer prints out. And the computer will do a good job of printing that out. It'll calculate it correctly. It's just using the wrong formula. So it's giving you the wrong answer. And so what we end up with is, therefore, the variance is biased. All right. So we get an unbiased slope coefficient, but we get a biased variance estimate. And so therefore, the confidence intervals and t-statistics will be wrong. So you'll get your slope coefficients will be fine. They'll be the same. They're not changed from OLS, but your the variances will be incorrect, and that means you get the wrong confidence intervals and t-statistics. So what's the solution to that? Well, I'll tell you the one the textbook talks about most. However, it isn't really the one that is most widely used. So the solution there are two solutions. One is use weighted least squares, which is also called generalized least squares, or use something called an HCE, which we'll talk about. That's a heteroskedasticity consistent estimator. I'll write that out when we get to it. All right, so what do we do here? Suppose we know the omegas. Suppose we know what's driving the variation in the variance, the heteroskedasticity. Then you could do this. You could define y star equals y over omega, and x star equals x over omega, and then we will call epsilon star, meaning epsilon over omega. And then if you estimate your regression, y equals x star beta plus epsilon star. So if you run the regression like that, then the variance of epsilon is, well, that's how we defined it. So it's the variance of epsilon over omega. And so that means, and here we're just looking at a single observation, so we can pull out the omega, but we square it, times the variance of epsilon. So that is 1 over omega squared times omega squared times sigma squared, and those cancel, and we're left with a constant. So what we've done is we've rescaled the data. So we've decided which is the variable that likely explains the pattern of the heteroskedasticity, and then we divide through the data by that variable. But the key thing is that we specified back here, we specified this with omega squared. If we had written it as just omega times sigma squared, you might have been wondering why we didn't. But suppose that we'd used omega times sigma squared. Well, that would be fine. Then that would just mean we divide through by the square root of omega. Because here, the key step is that when you get to the error term and you take that out of the variance sign, you have to square it. So you're applying a weight here, which is the square root of the variable that you think drives the variation in sigma squared. Because when you take it out of that variance operator, you square it, and then that's how it cancels out. So if you think about our education data set example, if it's GDP that we think is driving the heteroskedasticity, if we think it's GDP, as GDP goes up, that's where you get this spread in the data. You could do a couple of things. So you got education equals, well, let's make it alpha plus beta 1 GDP plus beta 2 population. Okay, in a data set like this, if you wanted to do what I just showed you, which is try to isolate the variance and make it constant, you could divide through by the square root of GDP. And you have to divide everything through. So the constant term then becomes 1 over square root of GDP. You divide GDP by the square root of GDP, and you divide population by the square root of GDP, and then that implies the error term is also divided by the square root of GDP. And again, why the square root? Well, that's so that if the variance of epsilon equals GDP times sigma squared, then the variance of epsilon over the square root of GDP equals 1 over GDP times GDP sigma squared, and so those cancel out. And we're left with a constant variance. So if that's the specific form that drives our heteroskedasticity, then this transformation will give us a regression with a constant variance. And so this is called generalized least squares. The book also uses the term weighted least squares because we're weighting each of the observations. And there's a fair amount in the textbook about this. Let me just pull it up over here. All right, so we've gone through this part. If that's the form of our heteroskedasticity, that's the variance. And then a generalized least squares estimator involves figuring out what that omega term is and applying it, and then you get a constant variance. And then that in turn means that the slope coefficient is a little different because you got that variance dividing through top and bottom. So then when we don't have the omegas, which is the usual case, what you do is you pick one of the variables in your data set, either on its own or in combination. You might make it a function of it, but you're going to use it to construct the weights. And this is where the textbook is now a little old-fashioned. Okay, because the problem is with a data set of any size or any complexity, you might fix the heteroskedasticity, but you might not, and you might just introduce a different form of bias to the variance when you do that. So we don't really recommend this kind of guesswork, this trial and error. In this case, you could apply a transformation that makes sense. And by that, I mean, for example, put the data into per capita terms. So then the model would be education spending per capita equals alpha plus beta 1 GDP per capita. And then you don't have population per capita because that's just 1. And then you'll have an error term. So if you had heteroskedasticity in the original model, so if this was the one where you had the problem of heteroskedasticity, and I haven't talked yet about how you test for it. We'll do that actually in the next lecture. But let's say you run a test for heteroskedasticity and it says, yeah, this one, you've got a heteroskedasticity, so you're going to get a biased variance. You should expect you'll get heteroskedasticity in a model like that. It would just make sense that you would. But education per capita and GDP per capita, well, you've now put the data on a more consistent scale. And so you're less likely to have heteroskedasticity in a case like this. So what we're going to do is not really focus so much on generalized least squares, that is, trying to find one of these clever transformations that gives you a constant variance, except in a case where there's an obvious transformation, one that just makes sense. And the most typical one is per capita terms. So if you've got data on house prices in the city of Toronto, and you have floor size is one of your variables. house price, PI, and then you got a whole bunch of the covariates, the kind that we've talked about, but it includes floor size, which is measured in square footage. Well, in a city like Toronto, you're going to have, you have condos that might be as small as a couple of hundred square feet, and then you've got mansions that might be 8,000 square feet. And so again, you have a wide spread of the scale in the data. So in that case, what you could do is look at trying to explain price per square foot. And then in that case, chances are your explanatory variables, you can have variance in them, but you're not going to have that big triangular spread of the data. So this would be a case where there's another obvious transformation. Price per square foot. Or if you were looking at, I don't know, crime rates by city, and you've got 100 cities and it varies from 2,000 or 3,000 people at the low end up to 5 million people at the high end. Well, now again, you've got this huge spread of the scale of the data. And that's where you get heteroskedasticity. That's where it just wouldn't make sense to not have heteroskedasticity because you've just got the data spread out so much. So again, in that case, turn it into crime rates per capita. Or let's say COVID infections by city or county or country. Doesn't make it's not informative to say, well, Canada has, I don't know what, we have 150,000 cases over the past 6 months or something like that, and the United States has 1.3 million cases, or whatever the numbers are. What you want to know is cases per capita or cases per 100,000 people, or some way of rescaling it so then the numbers are then comparable. And they're comparable because you put them on a scale where it makes sense. So if heteroskedasticity is present, and again, I haven't told you yet how to test for it, but we will get there. If heteroskedasticity is present, look for an obvious transformation of the data. For instance, making it per capita. Another transformation that might work is to take logs, and especially in time series, stock market data, for instance. If you're more interested in growth rates or rates of return, sometimes taking logs is a suitable transformation. So per capita, per square foot, and see if that fixes it. If that doesn't work, then we use option 2. And option 2 is a heteroskedasticity consistent estimator. Heteroskedasticity, and it's an estimator of the variance. All right, now, what do we mean by a heteroskedasticity consistent estimator? Well, just gonna dig up my notes here a little bit. Okay, so the term consistency is a statistical term. It means that as n goes to infinity, bias goes to 0, and variance goes to 0. So we've talked about having an unbiased estimator. So you know that if all the classical assumptions hold, the OLS estimator is unbiased. Sometimes we've got estimators that in small samples, they are biased. We know that they're biased, but the bias goes to 0 as the sample size gets large. We saw an example of that with the maximum likelihood estimator of the variance. So that's the sum of the squared errors divided by n. It's a little wrong. It should be n minus k. But if you have an extremely large sample, that bias will go to 0. So if you have an estimator that has these properties, that its variance goes to 0 and the bias goes to 0 as n goes to infinity, it's called a consistent estimator, as opposed to an unbiased estimator. So it's possible to write down a formula for the variance of beta that it's consistent. So in a small sample, it's still biased, but the bias goes to 0 as the sample gets very large, and the variance goes to 0, which means essentially the estimator collapses on the true value in a very large sample. In the book, the discussion is organized by supposing, or asking, what if we use the residuals from the regression to estimate the variances of the errors? In other words, can we use the square of the residual term to stand in for the unknown variances? If we did that, and we used the formula like this, so we estimate the variance of beta using the sum of xi squared epsilon hat squared over the sum of xi squared all squared. So those are the OLS residuals. Well, it can be shown, and it was shown back in the 1980s by a very clever econometrician named Hal White, that this is a consistent estimator of the variance of beta hat. And so the key in White's argument, or in White's proof, is that we don't actually need an estimate of epsilon by itself. In the formulas, we actually only need an estimate of x times epsilon. And when we use the OLS residuals, they give us a consistent estimator of that product of x squared times epsilon squared. And so as the sample size gets very large, this expression converges on an unbiased estimator of the variance regardless of the form of heteroskedasticity. So see, this is a consistent estimator of beta hat. Therefore, it is called an HCE method. Heteroskedasticity consistent estimator. It's consistent regardless of what drives the heteroskedasticity in the sample. Now, this is a funny little area of an introductory econometrics course, because one of the reasons that textbooks like this one still go through GLS, it goes through the whole explanation of how you can do a weighted least squares transformation and get rid of the heteroskedasticity problem. Because you have enough theory, you have enough math, we can go through it. So you know enough at this point to follow the discussion of GLS. But there isn't a lot of point in learning GLS anymore, because that's not how people deal with the problem. People deal with the problem using an HCE estimator. And it's very simple to implement, actually, in R or in any other stats package, as I'll show you. It's very simple to implement. The challenge, though, is the underlying theory is extremely complex, as you can imagine. You have to wait until you get to a graduate course in econometrics to go through the white article. But it's a nifty solution. And there'll be a similar issue that comes up when we look at autocorrelation later on. I shouldn't have mentioned that. You'll see what I mean. There'll be an autocorrelation consistent estimator that we'll get down the road. But for now, just we're focused on heteroskedasticity. So it's a situation where we have a solution that the computer can implement very easily, and it's a remarkable category of computational solutions, because, as I mentioned, HCE works regardless of the form of heteroskedasticity. What do I mean? For instance, why did I say that? Well, let's go back to our educational data set. Beta 2, population, plus errors. Now, I was assuming that GDP drives the heteroskedasticity, but maybe it's population. So maybe the reason that the variance explodes is population, or it might be some combination of the two, or maybe it's something else entirely. Maybe it's a variable we don't even have in the data set. But we did the transformation education per capita. Maybe it should be education divided by the square root of GDP, or maybe it should be education divided by GDP times population. Once you start taking your data set and trying to figure out the weighting scheme to get rid of heteroskedasticity, you may have a lot of choices, and it may not be clear which one is the right one. It may be a couple of different ones all get rid of the heteroskedasticity, but they end up giving you very different beta coefficients, which can also happen. So when you go with the GLS, or weighted least squares method, another problem is sometimes you change the beta coefficients and then you're not sure which is the right one to use. And also it can be very time consuming. If you have a data set with 6 or 7 variables, And you have to start testing all the variables, the square roots, the cross products, all that. Then it gets impractical, and nobody likes that. Just takes a lot of time. So what we would now do, what we now recommend, and what is in the newest textbooks, is try an obvious transformation. So I mentioned before, divide by population. It could do education spending per dollar of GDP, but then you've got a variable population over GDP, which doesn't really make a lot of sense. But education per capita and GDP per capita, they make sense. So you can use those. If you still have heteroskedasticity, then you apply the HCE formula. And then that'll work just fine. And if you, in the model that you're estimating, if you really want the coefficients in these forms, so you actually don't want to transform this at all, well, you can still apply the HCE method and you'll get a heteroskedasticity consistent variances of these coefficients. How you actually do it. Okay, so how to do it. Run OLS to get alpha hat, beta 1 hat, beta 2 hat. And then you just ask R to compute what are called White's HCE variances. And then R just knows apply the, there's a matrix version of the White's formula, and it's a bit longer than the OLS formula, but it's it just uses the matrix version of the formula that I just showed you, and it will then give you heteroskedasticity consistent variance estimates. The place to see it is if you look in our tutorial. Let me just call it up here for a moment so I make sure that I have the right page. So you're going to look in section 8.2.3 in the manual, and there's a few steps involved. This is an area where other packages like Stata, they make it easier than R does. You have to, it's a few more commands in R. But if you go through section 8.2 of the RStudio tutorial, I construct an artificial data set there just to give you an example of what heteroskedasticity looks like, and then go through the tests, which we're going to do next lecture. Go through the tests, and then when we get to 8.2.3, that's the commands there to calculate White's variance matrix, and then get the new t statistics from that. And then in 8.2.3, there's another HCE estimator called Nui West. You can leave that aside for now. That's the one that we'll use in the autocorrelation application. Now, one final point about the HCE approach, and the reason that it's still in textbooks, even though, as I've said, we appear to have this magic solution that saves a lot of effort. If by any chance you did know those omegas, if you had some way of knowing this, then it is true that GLS will give you the most efficient possible solution to heteroskedasticity. So if we know omega, well, squared, but we don't square it. If we know omega with certainty, GLS is blue. So if you are in a situation where you know the exact form of the heteroskedasticity, then GLS is the most efficient estimator. Since we're never really in that situation, this is the practical alternative. Apply a transformation that makes sense, and then otherwise run the HCE solution. So what do I need you to know out of the textbook? So you can follow all these steps. So we've gone through them. GLS by transforming the model. This is just a repeat of what we've already done. So this is just divide through by omega, and then you get the transformed error term that has a constant variance. Z just refers to taking a variable in your data set, or even a function of the variables in your data set, and using those, and then that gets into, well, how do you know the functions? Trial and error, try a million things, see if you find something you like. But then we get to discussing the heteroskedasticity consistent estimator, and you don't need to know that formula. You don't need to know the White's formula. At this point, we just sort of say, we're going to hand it over to the computer, and the computer will calculate the HCE, and it's consistent in a large sample, it's unbiased, and it's not as efficient as GLS, but GLS in most cases is not available to us, or at least we don't know that we have a GLS estimator. And then let's see, there's one more, the feasible GLS estimator, which we're not going to use that. That's another case where it works if you happen to know that that's the correct solution, but you don't have any way of knowing if it's the correct solution. So nobody does feasible GLS. And then next class, we will go into 5.3.3 and look at the tests for heteroskedasticity. All right, see you next time.